Hi everybody, in this next set of videos, we're going to look at polynomial and rational inequalities. So that word inequality means the same thing it always has, but we're looking at sort of equations, but instead of equal signs, they have less than, greater than, less than or equal to, or greater than or equal to. In solving polynomial and rational inequalities, the processes are very similar together, but they're actually quite different than when we did linear inequalities. If you think back to linear inequalities, we just worried about flipping that inequality symbol if we multiplied or divided by a negative. Otherwise, the solving process was very similar to solving equations. And that's not true with polynomials and rationals. It's actually a bit more complicated. So what I have for you is a set of steps that you're going to follow in order to correctly solve inequalities. So the first thing that we actually do here is we do want to make sure that one side is equal to 0. And we solve that inequality first. The real solutions here are going to be our boundary points. And what we're going to do is we're going to put these boundary points just on a regular number line. And that's going to divide the number line into intervals. And then what we're going to do is we're going to test a value on each of those intervals. And what you do is you plug it into your function. And what you're going to see is that on the interval, either you're going to get a positive result or a negative result. And actually, any value on that same interval would all be positive or all be negative. And then that's going to allow us to actually solve the inequality that we set equal to 0. So you'll have either less than 0, greater than, less than or equal to, or greater than or equal to. So I think it'll be easier to see with an example. So let's go through one now. And then I also want to show you how to check with Desmos, so to see how this works graphically. So here's our starting polynomial inequality. And again, it's easiest to solve when you have that one side equal to 0. So that's going to be your starting point. So I want to bring this 15 over, and I'm going to go ahead and subtract it from both sides. So I'm going to start with 2x squared plus x minus 15 is greater than 0. Now you're actually going to solve the equation version instead. For now, we're going to come back to the inequality at the end. And you want to think that for us, for solving, for polynomials, our main strategy tends to be factoring. So that's probably going to be what you're going to try first. If you have a quadratic, you can also use other techniques such as the quadratic formula. So you want to use whatever you have to solve at this point. Now, this one is actually factorable. Okay. And then we're going to factor it as 2x, let's see, minus 5 and x plus 3. I'm just checking my notes here. So the 2x squared only breaks down to 2x and x. 15 can be 1 times 15 or 3 times 5. So the combination that works here is going to be that 3 times 5, but we do want to make sure we set it up so we have that plus 1x in the middle. If you're using a factoring strategy and you're not very confident in your factoring ability, always make sure to check before you go further. So multiply this out off to the side. Make sure you do get that original equation. You don't want to spend all the extra time doing more work if your factoring is wrong. Once you have those factors, we set them each equal to 0, and we're going to solve. So here I have 2x equals 5, and I'll divide by 2. So I have x equals 5 halves. Now, if it helps, you can put this into decimal form, just so you know where it is on the number line. And then here we're going to subtract by 3. And I'm just going to draw a number line. Okay, and I'm going to put on my 2 boundary points. So I have one boundary point at -3. And I have the other boundary point at 2.5. So it'd be like right here. Now what happens with polynomial equations is that in between, so these are your values when they equal 0. So these actually would be x-intercepts on your axis here because they're real values. So in between, your polynomial will either be all positive or all negative on each of these intervals. So what we do is we pick a test value in each interval. And it doesn't matter which value you pick, as long as it's something in the interval. And for me, I usually try to pick whatever I think is the easiest. So smaller numbers or 0, things like that. So I'm going to pick -4 for this interval. I'm going to pick 0 for the interval in between. And then for the interval on the right, I'm going to pick 3. And what you're going to do is you're going to go back and plug it into this inequality. So we are really focusing on that 0 on the right-hand side piece here. So for the first one, if I plug in -4, make sure you do the square first. That's going to be positive 16. So I have 32 minus 4 minus 15. And what I get here is going to be 13. And this is positive, right? So what we see is that right over here, this interval is going to be positive. When I plug in 0, I always like to choose 0 if I can, because it's usually pretty easy to plug in. Most things cancel out. I get a negative. So the interval in between would be all negative. And then if I plug in 3, let's see, 3 squared is 9 times 2 is 18 plus 3 minus 15 is going to be 6, which is positive. And you don't really even need to know the final answer. You just need to know if it's positive or negative. That's really what we're looking for here. Now, to answer the question, you do want to go back to your problem. So our problem wants strictly greater than 0. So if you think about that, greater than 0 means we want positive, right? So where are answers positive? Well, they're positive from here to here, and they're positive from here to here. Now remember that this number line goes on forever. So the positive section is going to be from -infinity to -4. Sorry, not -4, -3, excuse me, I'm reading that wrong. -3, so I want to end with my boundary point. And then again, from 2.5, so 5/2, all the way to the right, going towards positive infinity. So this is going to be our answer. Now I am using parentheses on my endpoints because this is strict greater than. Your boundary points are where you are equal to 0, so you want to be careful about the problem. If you have strict greater than or less than for polynomials, then you're using parentheses on those boundary points. And again, if you want to draw in that number line, 1, 2, 3 solution here, you would go from here to here, and then from here to here. So that would be your answer, just graphically on a real number line. Now, let me show you how it works in Desmos too. And in Desmos, I'm going to focus on this form first. I think, again, keeping that 0 on the one side is probably the easiest thing to look at. Because, again, we're solving where is this positive. So let's look at Desmos. There it is. Okay. All right, so our equation was 2x squared plus x minus 15 . Oh, I haven't turned it on. There we go. So here is our graph. And remember, we're looking for, if you remember this problem, it was greater than 0. So look at here are our x-intercepts that we found. The first one was at -3, and the other one was at 2.5, which we saw. And notice that the graph is positive, meaning it's above that x-axis here, right? So it's positive when x is negative or less than -3, and it's positive when x is greater than 2.5. So it's the same solutions that we just had. We're looking for the part that's positive or above the axis. Now, if you want to look at the original function instead, just to show you how this works, I'm going to turn this one off. The left side of the function was just 2x squared plus x, and the right side was 15. So it's a similar idea here, but in this case, you're looking for greater than 15. And you can see that those two x values are still -3 and 2.5. That's where they would intersect. And if you go above 15, then you do have the x values less than -3 and greater than 2.5. So this is the graph using the original function with the left side and the right side graphed separately. So you still have that same idea. You're going greater than 15 here. So you're looking above that line. And this is another way to do it graphically. So I thought it was worth showing you this as well. However, for me, I do think it's easier instead of graphing each side separately to move everything to that one side like we did and then focus on that 0 line. So you can use either strategy to check for graphing, but you'll see that I tend to focus on kind of moving everything to one side as a little bit easier to see. All right, let's do another example here. So here we have another polynomial. And again, I want to get everything to one side. So I'm going to subtract the 1. I'm going to add the 2x. So I have 4x squared plus 2x minus 1 is less than or equal to 0. And I'm just writing everything in order. So with polynomials, we do like to have things with descending powers. Now, for me, the first strategy I would try is factoring. Again, if you have any polynomial higher than a square, that's really the only strategy you know. If you have a square, you do also have the quadratic formula as another very common strategy. So here, if you try to factor, it actually is not going to work. It's not a factorable polynomial. So I can use the quadratic formula here. But remember, that only works if you have a highest power of 2. So to review, it was negative b plus or minus the square root of b squared minus 4ac all over 2a. So our a here is 4, our b is 2, and our c is negative 1. So I'm just plugging in all my values. Watch your signs. That's kind of the hardest part here. So 2 squared is 4, and then 4 times 1 is 16, and those two negatives will cancel. So you end up with negative 2 plus or minus the square root of 20 over 8. Now the square root of 20, we can simplify, right? That's root 4 times root 5. 4 times 5 is 20. And then root 4 we can write as 2. So I can simplify this a little bit more. And then I can split into 2 parts. So I have negative 2 over 8 plus 2 root 5 over 8. And then I also have negative 2 over 8 minus 2 root 5 over 8. Simplifying these fractions a little bit more, 2 eighths becomes 1/4. So negative 1/4 plus root 5 over 4. I don't really need the 1 here because I have that root 5. And then negative 1/4 minus root 5 over 4. So there are our 2 main zeros. Now, these are both real numbers. I know they look kind of weird, but as long as they're real numbers, we can put them on the boundary line. If they were imaginary, then we wouldn't, because they would not be x-intercepts. So what you would probably want to do here is take out your calculator and get an approximation so you know where these numbers actually belong. And then for this one here, negative 1/4 minus root 5 over 4, this is about negative 0.8. And then for this first one ends up being about positive 0.3. So again, you don't have to be exact here. We do have our final exact answers, but I do need to know how to graph them on my boundary line. Okay. So negative 0.8 is going to be about right here, pretty close to negative 1. And then positive 0.3 is a little bit closer to 0. And then what you're going to do is pick a value in each of the intervals. So there's one interval here, right to the left of the boundary point. So I'm going to choose negative 1. In between, I'm definitely going to choose that 0. And on the right, I'm going to choose positive 1. And again, I'm just picking the easiest value I can in each interval. And you're focusing on this formula when you're solving rather than the original. So do make sure that you haven't made a mistake in the beginning steps. So I'm going to plug in negative 1. So negative 1 squared is positive 1, and then times 4 is 4. Here I have minus 2 minus 1. So I end up with 1, which is positive. So this area here is going to be positive. When I plug in 0, most of my values cancel. I have -1, so my middle area is negative. And then when I plug in +1, 1 squared is 1 times 4, and then here I have 2. So 6 minus 1 is 5, so I have a positive over here. Now, do check. I will note that all of our examples, we tend to go positive, positive, or negative, negative. They sign switch back and forth, but that's not always the case. It is possible to have positive, then positive again, and then negative, or even all positives or all negatives. You have to check each interval individually. And that's because, remember, sometimes when we have x-intercepts, the graph doesn't go through the axis and may bounce back up. So you want to be really careful there and still check each interval. It doesn't mean it always switches back and forth. So here, now we're ready to answer the question. We want to go back to our problem, and it was less than or equal to 0. So our options here are negative is good, right? Less than, or it could actually be equal to 0. So the region where I'm negative is right in between here. I do want to include where we're equal to 0. So I actually am going to include those endpoints this time because that's where our values are 0. So my answer, and I'm going to use the actual root form here. So the negative 0.8 is -1/4 minus root 5 over 4. And then the positive 0.3 was -1/4 plus root 5 over 4. So our interval notation would look like this for our solution set. Again, I'm using brackets here because I do want to include those end values because we are including 0 this time. So I do want those end points. As a little side note, if you also wrote this as, let's say, -1 minus root 5 all over 4, or same thing with the plus, that's correct too. So you could write that answer in either form. Now, for the graph, I'm running out a little bit of room here. So I'm just going to do it kind of right on this. What would happen is you would have the bracket here, right? And you'd have a bracket here, and you would be shading in between. So you want that in between area of your graph, and we would be using brackets on both sides because we're going to include those ending points. So this part of your graph would be shaded in. All right, I'm not going to check this one on Desmos, but you can check it yourself. So if you graph this right here, you're looking for the part of the graph that's below the x-axis, right? So either 0 or below. And you should see that that happens between these two values. That's where that graph is going to drop down. All right, and let's do one last example here with polynomials. Again, I want to bring everything to the other side. So I'm going to subtract 4x and subtract 4. So I start with x cubed plus x squared minus 4x minus 4 is less than or equal to 0. And again, I'm writing everything in order here. Now, I do have a cube, so I can't use the quadratic formula or anything like that. I'm going to have to rely on factoring. And if you see 4 terms, the way that you're probably going to end up factoring is factoring by grouping. So what we do is we group our first terms together and our last terms. Now, I do like to put a plus sign in the middle and keep the signs with the numbers. I find that to be easier. And here we take the GCF out of each group. So the GCF here would be x squared, and I'd have an x plus 1 left. Here the GCF would be -4, and I'd have also an x plus 1 left. If grouping works, you would have this x plus 1, or whatever factor it is, written over the same factor twice. And you take that out one last time, and then you go ahead and rewrite what is left over. Now, actually, when I'm solving, I should really switch this to equal sign. It doesn't really matter as you're doing your work, but I'll switch it now just to make it a little bit easier to follow. And I do want to factor this a little bit more. I can factor that into x plus 2x minus 2. So here I'm going to have, in this case, 3 boundary points because all 3 are real numbers. These would be your x-intercepts on your graph. Here I subtract 1, I get -1. Here I subtract 2. Here I add 2. So let's see, I have 1 boundary point at -1. I have 1 at -2, and I have 1 at +2. So we do have to pick our test values in between every interval. So on the right here, I'm going to pick 3. In between here, I'm definitely going to pick 0. On the left, I'm going to pick -3, and then I do need something in between here. So I'm going to pick whatever I think is the easiest. So maybe -1.5, right? Kind of halfway in between. So I do need a test point within each interval. And then we're going to go ahead and plug those in. So when I plug in -3, again, go back to this one right here. I have -3 cubed plus -3 squared minus 4 times -3 minus 4. -3 cubed is -27. This would be +9, +12 minus 4. And what you get is -10. So we get a negative here. I'm going to save the 1.5 to the end. Let me plug in 0 next. So I have 0 cubed plus 0 squared minus 4 times 0 minus 4. So this is going to be -4. So negative. When I plug in +3, I have 3 cubed plus 3 squared minus 4 times 3 minus 4. So I have 27 plus 9 minus 12 minus 4, which you get +20. And then for the last one, now I tend to like fractions more because they are often more accurate, but I don't need exact answers here. I really just need if it's positive or negative when I plug it in. So feel free to use the decimal in this case. Again, if you like, even if you have to round, it doesn't matter as long as you know if the value is positive or negative. So I would do -1.5 cubed plus -1.5 squared minus 4 times -1.5 minus 4. And let's see, when you do all that, you're going to get 0.875. So it is positive. And I just used my calculator there. Now, our answer here is all about less than or equal to 0 again. So I'm looking at negatives or 0. So I want this area and I want this area. I'm looking at equality as well, so equal to 0. So I'm going to include my boundary points here. So my answer is going to be from -infinity to -2. And then again from -1 to +2. So I have this interval here going -infinity all the way up to the boundary point of -2. And then from -1 all the way to 2 here. Again, I'm using brackets in this case because we are including 0. So I'm including those endpoints. If you're looking at the graph, I have a little bit extra room, so I'll redraw it. Let's see, 1, 2, -1, -2. We're going between 1 and 2, or -1 and 2, excuse me, and then we're going less than -2. So your solution set on the graph would look like that here. Again, you can check it on Desmos yourself, and I really encourage you to do this. So plug this into Desmos, and you should notice that that graph falls below the x-axis on these two different intervals. So it falls below here, and then also falls below here.